Hello everyone, and thanks for watching Edupedia World. In this video, we are gonna learn about relations and functions. The main contents include ordered pairs, Cartesian product, number of elements in Cartesian product, relation, functions, vertical line test, domain and range, graphs of basic functions, and algebra of real functions. Usually, we'll follow a step-by-step procedure to understand a chapter, but for understanding relations and function in a better way, we'll have an overlook to entire thing that we are going to study in this video, and then come back and follow step-by-step procedure. That is, look each and every topics in a detailed manner. Before that, what is a relation? Relation in general aspect is nothing but connection between or among things. Each relation has a pattern or property, and it involves a minimum of two identities. Everything in this universe is related to each other. If we take two objects which we think are totally unrelated, still they will have some common relations. Let us discuss a practical example. Imagine tossing a ball straight up into air, watching it rise, stop, and fall back down in your hand. As time passes, the height of the ball changes, creating a relationship between the amount of time the ball was in the air and its height. That is, at time equals 0, ball is in your hand, and at time equal to 1 second, it might have reached a height of, say, 2 meters. In mathematics, a relation between variables that changes together, such as time and height, is called a relation. Let us divide the screen into two. The first column contains name of greatest scientists, and second column some famous discoveries and theories. Then we'll try to find relationship between them. Let us relate the second column members as the discoveries made by first column members. Laws of motion and universal law of gravitation is proposed by Sir Isaac Newton. So the relation is clear, and we'll plot two arrows pointing from Isaac Newton to laws of motion as well as universal law of gravitation. Laws of motion and universal law of gravitation. Similarly, Albert Einstein is related to special theory of relativity. Geometrical representation of complex numbers was discovered independently by Caspar Wessel and Carl Friedrich Gauss. So, arrows from both these scientists will point to a common member in second column, precisely complex plane. Carl Friedrich Gauss also proposed divergence theorem. So, arrow from him will point to divergence theorem also. Now, we have found relation between all the members from both the columns. Here we can see that electron is being omitted. Electron was discovered by J.J. Thomson. Unfortunately, his name is not in column 1. In mathematical language, we can call the first column as domain and the second one as codomain. Let's plot it here. The first column, the entire first column is called domain, and the entire second column is called codomain. Except electron, every other member in column is somehow related to members in first column. So they are called range. That is, laws of motion, universal law of gravitation, special theory of relativity, and complex plane. They all are range of first column. That is, all these are range of first column. With the previous knowledge we have our set theory, we can now say that range is a subset of codomain. Range being the subset of codomain. So far we found relation between first and second column members. Generally we'll have a doubt whether all these relations can be called as functions. The answer is no. A function is a special relationship where each input has a single output. In aforementioned examples, we can see that Isaac Newton is related to two discoveries, 1 and 2. That is, two arrows point out from him. Or in other words, we can say a single input gives two outputs. Same will be the case with Carl Friedrich Gauss. A single input gives two outputs. So these are not function. This is the basic overview of relation and function. Now we can go in detail. While learning relation, the first concept we should understand is about ordered pairs. The elements of a set are not ordered. For example, set Jupiter, Saturn and set Saturn, Jupiter are one and the same set in virtue of the principle of extensionality. If we want to sort the elements of a pair Jupiter, Saturn so that one of them is first and the other is second, we need the notation of ordered pair. If A and B are two sets, then pair of elements of A and B written in small brackets and grouped together in a particular order is defined as an ordered pair. Let P1 equals ordered pair AB and P2 equals ordered pair CD. P1 equal to P2 if and only if A equal to C and B equal to D. That is, first component of P1 equals first component of P2. Similarly, second component of P1 must be equal to second component of P2. Once we have ordered pairs, we can talk about sets whose elements are ordered pairs. For example, given any pair of set AB, one can form the Cartesian product A cross B, which is implicitly defined by P belongs to A cross B, where P is an ordered pair whose first component belongs to A and second component belongs to B. In set builder form, A cross B equals set of all ordered pairs xy such that x belongs to A and y belongs to B. That is, let's take an example. Let A equals set of 1. Let it be a singleton set, and consider another singleton set B. B equals set, say, n. Okay, so A cross B equals set of all 1, n in ordered pair notation. So the first component, that is this 1, is from set A, and the second component is from set B. Now let us take an example. Let A equals set of all x, y, z, and set B equals set of all p. Okay, now let's find A cross B. A cross B equals set of all, first component is from set A and second component must be from set B, like this. Okay, so let's write them in ordered pairs. xp, yp, zp. Okay, now let's write B cross A. B cross A equals set of all b, x. Here the first component should be from set B because it is B cross A, like this. B, x, p, y, and p, z. We can clearly see from above that A cross B not equal to B cross A. A cross B will be equal to B cross A only when A equal to B. Okay, let's see that. Let A equal to set 1 and B equal to set 1. Now A cross B equals first component from set A and second component from set B, that is set of all ordered pairs 1 1. Similarly, B cross A also equals set of all ordered pairs 1 1. Here we can see A cross B and B cross A are identical only because A and B are equal. Take another example. Let A equals set of all 1, 2, 3. B equals set of all 3, 4. And C equals set of all 4, 5, and 6. Here we shall find A cross B intersection C. A cross B intersection C. So for that, first let's find this B intersection C. B intersection C equals set 4 because B and C has only one element in common, namely 4. Therefore, A cross B intersection C equals set of all ordered pairs 1 4, 2 4, and 3 4. So that's the answer. Now let us consider another example. Let us find A cross B intersection A cross C for the same question. From above, we can see that A cross B equals set of all ordered pairs 1 3, 1 4, 2 3, 2 4, 3 3, and 3 4. And A cross C equals set of all ordered pairs 1 4, that's 1 4, 1 5, ordered pairs 1 6, 2 4, 2 5, 2 6, 3 4, 3 5, and 3 6. So now we have to find the intersection, that is the common element between A cross B and A cross C. Therefore A cross B intersection A cross C equals set of all ordered pairs. So what are the common elements in these two sets? 1 4, 1 4, comma, then 2 4, 2 4, comma, 3 4. So this is the answer. Now let us find the number of elements in a Cartesian product. If A and B are two finite sets, then number of elements in A cross B is equal to number of elements in A multiplied by number of elements in B. That is, n of A cross B equals n of A into n of B. So let's take an example and prove the same. Let A equal to set 3, 4, 5, 6 and B equal to set x, y, z. So n of A is 4 because the number of elements are 4 in set A, 1, 2, 3 and 4. Similarly for B, the number of elements are 3, 1, 2 and 3. So n of A cross B equals n of A into n of B, which is 4 into 3, that is 12. If we write an ordered pair of A cross B, we can see that A cross B equals set of ordered pairs 3x, 3y, 3z, 4x, 4y, 4z, 5x, 5y, 5z, 6x, 6y and 6z. And if we count all this element, we'll get 12. Relation. Let A and B be sets. A binary relation from A to B is a subset of A cross B. A relation R from a set A to a set B is a set of ordered pairs AB where A is a member of A, B is a member of B. The set of all first element is domain of the relation. The set of all second element is the range of the relation. In other words, for a binary relation R, we have R is a subset of Cartesian product A cross B. We use the notation ARB to denote that the ordered pair AB belongs to R. Let us do a practical example. The speed of a racing canoe in still water varies directly as the square root of its length. If 16 feet canoe can travel 6.2 meter per hour in still water, find a variation model that relates the speed of a canoe to its length, and also find speed of a 25 feet canoe. So let's have the solutions. Let S represent speed of the canoe and L represent the length. The general variation model is S directly proportional to root L. That is, in question it is mentioned that the speed of racing canoe in still water varies directly as the square root of the length of the canoe. So S directly proportional to root L. Or we can write S equals some constant K into root L. To change proportionality to equality, we introduce a constant K. It is given for 16 feet length, canoe can travel 6.2 km per hour. 6.2 meter per hour. So 6.2 equals K into root 16. Root 16 is 4. So we have the value of K as K equals 6.2 divided by 4. That's root 16. That is equal 1.55. So we have the relation S equals 1.55 into root L. This is the relation. That is, this is the variation model that relates the speed of the canoe to its length. Now we can look into second question. That is, find the speed of 25 feet canoe. So let's take this equation again. S equals, we know the value of K, that is 1.55. we have found it here. So 1.55 into root L. Okay, if length is 25 feet, that is, substitute for length. S equals 1.55 into root 25. Root 25 is 5. So we have S equals 1.55 into 5, which is same as 7.75 meter per hour. And don't forget to write the unit, especially for numericals. Now let us discuss about functions. A function is a rule which maps a number to another unique number. In other words, a function f is a relation from a non-empty set A to a non-empty set B such that the domain of f is A and no two distinct ordered pairs in f have the same first element. So let us discuss that. If f is a function from A to B, f is a function from A to B, and ordered pair AB belongs to function f. Ordered pair AB belongs to function f. Then f of A equal to B. F of A equals B, where B is called the image of A under the function f. B is called image. Similarly, A is called the pre-image of B under f. A is called pre-image. Let us simplify this. If we start off with an input and we apply a function, then we get an output. Let x be the input which we are providing into a function machine f, so that we'll get an output f of x. the variable x is called argument. This is argument. And the variable f of x is called range. Okay. X is also called independent variable because it is unaffected variable, whereas y is affected by variable x, and hence it is called dependent variable, which is a result of the function. If the value of x changes, we can have the corresponding change in f of x. Let us consider an example. F of x equals x square plus 2x plus 3. To evaluate a function at a point, say 1, f of 1 equals 1 square plus 2 into 1 plus 3. That is, everywhere in the place of x, we substitute 1. Here, 1 is called input and 6 is the output. So we get f of 1 equal to 6. This can be also represented as an ordered pair 1, 6. Domain and range. Recall what we have observed earlier in the definition of the function. X giving f of x. Here, x is the set of all allowable inputs and f of x is the set of all resulting outputs. Here, x is also called domain of the function and f of x the corresponding range of the function. Now, let us consider an example. Function f of x where f of x equals x square. Here, the domain of the function is all real number r. Consider another example, f of x given by f of x equals 1 divided by x minus 1 into x minus 3. Here, domain of this function is all real numbers except 1 and 3. The reason is, if we put 1 and 3 in the function, we'll end up in division by 0, which is not possible. Therefore, domain of the function f of x equals 1 divided by x minus 1 into x minus 3 is minus infinity to 1 union 1 to 3 union 3 to infinity. 1 and 3 are not included. We can represent this in a number line and it will look like this. That is, a gap at 1 and 3 indicating that they are excluded from the number line. Consider another example. Function f of x given by f of x equal to root of x square minus 5x plus 6. It can be factorized into x minus 3 into x minus 2 under the root. Let us examine the domain of this function. In the previous function, the function won't exist when division by 0 situation arises. It should be dealt with care that when a negative number appears inside the square root, it gives rise to complex numbers which we are not dealing with in normal calculus. So, in the above function, when writing the natural domain, we should consider all real numbers where x square minus 5x plus 6 is greater than or equal to 0. In this case, the domain becomes negative infinity to 2 including 2 union 3 to infinity including 3. If we draw a number line, it will look like this. Let's summarize how to write the domain. First, avoid division by 0. Secondly, avoid even roots of negative numbers. And the last but not the least, meet the requirement of the problem. Example, In physical situation, when we are dealing with area, volume, perimeter and so on, we won't have negative entity, like there is no negative area or negative volume. So accordingly, we have to choose the domain to satisfy the physical requirements that can't be mathematically defined. Let us look into graphs of basic functions. The first one, f of x equals x. Here I substitute some values for x and got the corresponding graph. We can have the privilege of choosing any values between minus infinity to infinity for x. Therefore, the domain of the function becomes minus infinity to infinity. When we substitute for x, we'll get corresponding f of x values which has no limitation. That is, f of x can vary from minus infinity to infinity depending on x value. So, the range of the function is also minus infinity to infinity. F of x equals x square. We can choose any value for x. It can be negative or 0 or positive. Rather, any number between minus infinity and infinity. So, domain of the function f of x equals x square is minus infinity to infinity. When we square a real number, the result will be always a positive real number. Therefore, the output f of x will be always positive, making the range from 0 to infinity. This is pretty much clear from the graph. The graph exists in first and second quadrant only. F of x equals x cube. Here I plot some values for x and I got corresponding graph. We can choose any values for x and we get corresponding f of x value. So both the domain as well as range is minus infinity to infinity. F of x equal root x. We have already summarized the rules for writing domain. We can't have a negative entity inside the root. So x can have only positive values, making its domain 0 to infinity. Also, since square of a real positive number is never negative, we can't have a negative entity at output of a square root function. Therefore, range is 0 to infinity or simply all positive numbers. Consider the function f of x equals 1 divided by x. Here, x can take all values except 0 to avoid division by 0. So, the domain of the function is all real numbers excluding 0. Correspondingly, the range will be also all real numbers excluding 0. F of x equals absolute value of x or modulus of x. Here we can choose any value as input, that is, x can take values from minus infinity to infinity, but since it is a modulus function, the output value is always positive. So the range of the function is from 0 to infinity. Signum function. In mathematics, the sine function or signum function is an odd mathematical function that extracts the sign of a real number. In mathematical expressions, the sine function is often represented as SGN. SGN of x or signum of x equals -1 if x is less than 0, 0 if x equal to 0, and 1 if x is greater than 0. greatest integer function. The greatest integer function of a real number x is represented by f of x equals x inside the square bracket. For all real number x, the greatest integer function returns the largest integer less than or equal to x. In other words, the greatest integer function rounds down a real number to the nearest integer. The graph looks like a staircase, that is, a series of steps. So, the greatest integer function is sometimes called as step function also. One endpoint in each step is closed, that is, black dot to indicate that the point is the part of the graph, and the other endpoint is open or open circle to indicate that the point is not the part of the graph. Observe in the graph that in each interval the function f of x is constant. For example, the value of the function f of x remains negative 5 in the interval minus 5 to minus 4. We may have misconception regarding function. We may consider every graph to be a function. This is entirely wrong. Consider a relation defined by a set of points xy in a rectangular coordinate system. The graph defines y as a function if no vertical line intersect the graph in more than one point. That is, a curve in the xy plane is the graph of some function f if and only if no vertical line intersect the graph more than once. Example for a curve which is not a function. Let us consider a unit circle at the origin. Here, the vertical line crosses the point at two distinct points. Hence, the curve is not the graph of a function. Algebra of real functions. In this section, we shall learn how to add two real functions, subtract a real function from another, multiply a real function by a scalar, multiply two real functions, and divide one real function by another. The first, addition of two real functions. Let f from x to r be one function, f from x to r is nothing but real number, and g from x to r be any two real function where x is a subset of real numbers r. Then we define function f plus g. Function f plus g from x to r by f plus g of x equal to f of x plus g of x for all x belongs to capital X. Subtraction of a real function from another. Let f is a function from x to r and g is defined from x to r be any two real function where x is a subset of real numbers r. Then we define f minus g. We define a function f minus g from x to r by f of, I mean f minus g of x equals f of x minus g of x for all x belong to capital X. Multiplication by a scalar. Let f is a function defined from x to r and alpha be a scalar. Here by scalar we mean a real number. Then the product of alpha into f is a function from x to r defined by alpha of f of x equals alpha into f of x, where x belong to capital X. Multiplication of two real functions. The product or multiplication of two real function, say f defined by f from x to r and g from x to r is a function, then fg defined from x to r is defined by fg of x equals fg of x equals f of x into g of x, where x belongs to capital X. The last one, quotient of two real function. Let f and g be two real function defined from x to r. From x to r. And let x is a subset of r. The quotient of f by g denoted by f by g is a function defined by f by g of x equals f of x divided by g of x, provided g of x not equal to 0, that is denominator can't be equal to 0. Also x belongs to capital X. Let us do one problem. Let f of x equals x square and g of x equal 2x plus 1. Let this to be real function. Then let's find f plus g of x, f minus g of x, fg of x, and finally f by g of x. Okay, so we have f plus g of x equal sum of these two, that is x square plus 2x plus 1. Similarly, we have f minus g of x equals the first function x square minus 2x plus 1, that is x square minus 2x minus 1. The next one, fg of x, that is equal to x square into 2x plus 1, which is equal to 2x cube plus x square. Now the last one, f by g of x, which is equal to x square divided by 2x plus 1. Okay, but here we should make sure that x does not equal to minus 1 by 2. If x equal to minus 1 by 2, we have 2 into minus 1 by 2 plus 1, that is minus 1 plus 1, which is 0. Denominator can never be 0. Hope this video helps you to learn some basic concept on relations and function. For more videos, please follow Edupedia World. Thanks for watching and have a great day.